Welcome. This is our second lecture on network science for social media analytics. What we're going to do is to build upon the vocabulary that we already know about networks and try to define a little bit more advanced concepts that we're going to find useful in the rest of the course. So, first, to recap what we know so far, we've talked about different types of networks. We've talked about different ways to characterize the networks. This includes degrees, degree distributions, the connectivity of networks, the density of networks. We also talked about notions like centrality measures, the power law behavior of degree distributions, and we gave you two random graph models, the Erdős-Rényi model and the preferential attachment model, to simulate networks such that they exhibit properties that you might see in real life. In this lecture, we're going to focus on three additional areas. First, we're going to define something called the clustering coefficient. This is going to be a very useful notion that we'll build upon in future lectures. We'll talk about what it means for a network to be a small world, and there's a very precise technical way to define small world networks, and we'll talk about that. And then we'll talk about what do people do as a network scientist. So, if you want to do network analytics for social media, you need to think about typical applications, typical tasks that people want. And it's again good to have a vocabulary or terminology to define these tasks. So we'll focus on these items in this lecture. So first, let's talk about clustering coefficient. This is a very intuitive notion that you might see exhibited in media like Facebook and so on. Essentially, it captures the idea: is a friend of my friend also my friend, right? And Facebook, this is one of the tools that they use when they make you friend recommendations. When they give you friend recommendations, they're noticing that a lot of your friends are also friends of this new person, and therefore they make a guess that perhaps you might know this person as well. So maybe you want to connect with this person directly on Facebook. And it's very possible, it's very easy to quantify this notion mathematically, even though it looks a bit abstract. So look at these examples on the left. We have three graphs here, and let's look at everything from the perspective of this one node here, which is colored in blue. So everything that we're going to do in this slide is from the perspective of this one blue colored node. So let's look at the blue colored node, and the blue colored node has three friends or three neighbors, which are these three other nodes. And true enough, these three other nodes all seems to be friends with each other, right? So there are three nodes here. So there's a total possibility of three edges, and true enough, there are indeed three edges between those three nodes. So the clustering coefficient, as far as this node is concerned, is 3 divided by 3, which is 1. Let's take the second graph here. The second graph is the same as the first, except we have removed two of the edges. So they are just shown as dotted lines. You have to imagine the dotted lines as edges not existing, they've just been deleted. So once again, let's look at it from the vantage point of this node. This node has three neighbors. There are a possible total of three edges, but of these three edges, only one edge really exists, which is this edge over here. So the clustering coefficient is 1 by 3. In the bottom case, this is a case where blue is a friend with three nodes, but none of these three nodes are friends with each other. So the clustering coefficient is 0 divided by 3, which is 0. So the clustering coefficient of a node Ci of node I is essentially the proportion of node I's neighbors who are connected. So if node I has ki neighbors, then there's going to be a total of ki times ki minus 1 by 2. So if you have three nodes, it's going to be 3 times 2 by 2, which is 3. And that's why the 2 goes to the numerator. And you're taking that in the denominator and you're expressing that to see what fraction of actual edges are actually existing. And that's why you get 2e divided by ki and ki minus 1. So it's a very simple way to calculate the clustering coefficient of every single node. And if you want to find the clustering coefficient of the whole graph, of the whole network, All you have to do is compute the clustering coefficient of each node and take the average of all these clustering coefficients, or take the maximum of the clustering coefficients. Typically the mean is taken, so it's just the average. So when people say the clustering coefficient of a network is so and so, what they really mean is they've computed the clustering coefficient of each node, and then they have computed the average of all of those values. So that's what clustering coefficient means. So just keep in mind that because the clustering coefficient is a ratio, is a proportion, it's a number between 0 and 1. If it is a 1, it means it's a very highly clustered node from this node's point of view. If it is 0, it means this person is having a lot of separate relationships with nodes, but they don't seem to be having any relationships to each other. And one of the things that you can use clustering coefficient for is to think about how the network is clustered, as we saw on the previous slide here. You can view this as a notion of clustering, but you can also view it as an indicator of modularity and hierarchical modularity. So as an example, if you look at the slide here and look at the network on the left, you see here that there's a sub network of this network that's likely to have high clustering coefficient, because there seems to be a lot of edges going every which way, and there's a lot of edges going every which way here, and there's a lot of edges going every which way here, but there are very few edges going across them. So the clustering coefficient is probably high here, it's probably low in these parts, and it's probably high again in these parts. So this type of network is said to exhibit a structure of modularity, because it seems to be possible to break down this network into three parts, each of which has very high clustering coefficient, but there are very few loose links between them. In the second network on the right, this is also modular in a way, but it exhibits modularity at two levels. So that there's a big clustered network going on here, but then within this network there are like three little groups going on here, just like this. So this is an example where the network has what is called hierarchical modularity. It's almost like a tree diagram. On the top, there's one level of organization with these big groups here, and then you drill down into each group. There is a little bit more organization into each of those sub networks within that group. And one of the things you could do is you could define what is called the cluster function. And remember that the clustering coefficient is where you compute the clustering coefficient of each node and simply average them. But in cluster function, this function is a function of k, which is the degree of a node. So what you do is you find the clustering coefficient of all nodes with degree 1. And you find the clustering coefficient of all nodes with degree 2, all nodes with degree 3, and so on. And essentially you create a function where k is the degree and ck is the average clustering coefficient of all nodes having that degree. And if you look at the shape of that function, if that function looks like a power law, and remember we talked about power law in the context of degree distributions, but here you can talk about power law in terms of the clustering coefficient distribution. If that distribution follows a power law, this is sometimes used as a necessary condition or a definition of hierarchical modularity. And if you think about it, the reason this happens is there's going to be lots of nodes with there's going to be a certain set of nodes with a certain degree and a clustering coefficient, and there's going to be lots of nodes with certain other degrees and clustering coefficient, and so it's going to have the shape of a power law. And when that happens, it's often considered to be evidence that the network has hierarchical modularity. So right here we have combined two concepts. We have combined the concept of power laws, we have combined the concept of clustering coefficients, and we are aggregating the clustering coefficient across nodes that have the same degree, and using that as a way to define what it means for a network to be modular and hierarchical in nature. So that's about clustering coefficient. Let's get on to another concept in network science, which is called the small world phenomenon. And this is a term that you might have heard everybody remark, "Hey, it's a small world. I just ran into someone, and it turns out this someone knows someone else I know," and so on. But the term actually originated with this experiment done by Stanley Milgram, who was a professor in the 19th in the 20th century, 19 something, and he is known for doing a lot of wacky experiments. He's most notoriously known for conducting what are called these obedience experiments, which nowadays no human subject rights panel will approve that you conduct. But one of the nicer pieces of work that he has done is this work called the small world phenomenon. And what he did was he took letters, he put them in envelopes, and he gave them to people in different parts of the country. And he asked them, get this letter to its final destination by sending this letter to somebody you know. So he would give a letter to somebody in Nebraska, who's over, in the middle of the country, and he'll ask that person to send the letter to somebody in Massachusetts, but he won't give them the address of this person in Massachusetts. He would just say, "Here's this person, and this person lives in Massachusetts. Find some way to get to this person," right? And so this Nebraska person obviously may not know this Massachusetts person. This Nebraska person might know somebody in Ohio. The Ohio person will know somebody in New York. New York will know somebody here, and so on. And everybody is going to send the letter to someone who they think will know who to send it to. And these were real, actual snail mail letters, right? And then what he did was he tracked how many letters reached their intended destinations and how many steps they took. And of course, many letters did not reach their destinations because this is really difficult to predict who to send it to. But what was surprising was of the letters that did indeed reach their destination, the average length, the average hops they took was only six. And that's when the name 6 degrees of separation came about. That with 6 steps, you could reach anybody in the world, starting from anybody. So this was Stanley Milgram's experiment that sort of defined the notion of a small world. And if you're interested in history, you should check out some book about Stanley Milgram. He's done a lot of wacky experiments in his life. He used to ride on the New York subway. After he was denied tenure at one university, he moved to the City University of New York, and he used to ride the subway and do strange experiments on the people riding on the subway. So there's a lot of cool stuff that he's done, but in this course, we're going to remember him primarily for his small world experiments. And so, given this type of, so this slide basically summarizes what we just discussed. That given a target individual, you pass the message to someone who you know that you correspond with, who you think is closest to the target. And as you can see from the slide, only 20% of these chains really reach their final destination, and of the remaining one, the average was 6.5. And that was Stanley Milgram's work, but it's still an abstract notion of what do we mean by a small world network. Um, so this slide shows there are two basic characteristics that we need in a network to call it a small world network. The first characteristic is that it must really be a real world network, and real world networks have a high clustering. We talked about clustering coefficient. So networks are highly clustered, which means people tend to know each other. So the clustering coefficient of your network must be much much larger than, this is the symbol for much much larger than, the clustering coefficient of some random network with the same number of people and the same number of edges. So given those conditions, we would say that it has high clustering coefficient relative to a random network, and we think of that as one of the conditions for a small world network. But at the same time, while it has high clustering coefficient, we want it to have low average path length between nodes, like the 6 degrees of separation. If I were to pick two nodes at random in the network, the length between those two nodes must be really small. The average length, if I take all pairs of nodes. So the average shortest path length in the network should approximately be the logarithm of the number of nodes in the network, which means that at most uh, I should not take the full length of the network to reach a node. I should probably take a really few small number of hops, and that small number is denoted by this order of magnitude reduction that you would get by taking the logarithm, right? And what makes a small world network is both these two characteristics. And it wasn't clear how to create a network that had both these two characteristics, because these are like two contradictory objectives. And so, to understand this, let's look at this network here. This is what we would call a regular ring network. So, all we are doing in this network is we are laying out nodes along a circle. So, imagine every node here to be a person, and we are connecting each node to its four nearest neighbors. So you take this node here, this node is connected to this node on the left. It's also connected to a node two steps from it through this direct link here. And similarly, this node is connected to the node on the right and to another node two steps down by this direct edge. So it's sort of a ring where there are these really local neighborhoods. People seem to know each other locally. They won't know somebody on the other side of the network, but they know each other locally. And so this is an example of a network that has high clustering coefficient, but it also has high average shortest path, because if I have to go to the other end of the network, I'll have to literally travel pretty much the same distance except with some hops. But there is really no magic logarithmic reduction in length going on. I still have to go through pretty much a function of the number of nodes to reach it. So this is an example of a network with high clustering but also high average shortest path. Now look on the right here. This is the same nodes here. So all we are taking is take the same nodes along a circle and put the same nodes here. But now I'm going to do this Erdős-Renyi model. Remember we talked about it in the last lecture. I'm just going to toss a coin, and with some probability I'm just going to connect nodes randomly every which way. And when that happens, you get a random network. Now this network, because it's random, it creates a lot of shortcuts. And as a result of these shortcuts, the shortest path length is going to be really low. So it's going to satisfy the second condition, but now it's not going to satisfy the first condition because the nodes are no longer clustered. The neighbors of your neighbor are no longer your own neighbors. So here on the other extreme, which is a random network, we have the condition met for the average shortest path, but the condition is not met for the clustering coefficient. So what people did was, this was a very creative paper. It's a paper written by two people called Watts and Strogatz. Duncan Watts and Steve Strogatz. They were physicists. They're at Cornell. Steve Strogatz is still a physicist at Cornell. You might want to check out his Twitter feed. He writes a lot of cool things about maths and physics. But what Watts and Strogatz did was they viewed the left network and the right network not as two different types of networks, but as networks on a continuum. So what they did was they started with this ring network, this regular topology that I mentioned, and then they started rewiring some edges. And this is really important. So they will toss a coin, and with some probability, they will take an existing edge in this network. They'll take this edge, let's say, and they'll randomly rewire it. They'll rewire it, meaning they'll keep one edge of the network fixed, one end of the network fixed, of the edge fixed. They'll take the other edge and move it from its current node to some other node. So they'll do some, quick rewiring going on. So when the rewiring happens, the network starts to lose its regular ring property and starts to look more like the random network. So this is sort of a way to interpolate between the regular ring network and the completely random network, so that it still has some properties of the clustering that you saw, but now it starts to destroy it in some other places, and you start getting these crisscross random shortest path edges going on. And what is interesting was they did this rewiring in different levels. So on the x-axis here is the number of links that have been rewired, and this graph here is on a log scale. So you have to think about it from the viewpoint of taking 10 to the power of these values here. On the y-axis is basically there are two plots being shown. One is the ratio of the shortest path length. The other is the ratio of the clustering coefficient with respect to where you started out with. So initially, both of you start with a certain value, and then as you start rewiring, these values change, and you're tracking it. And the top graph is the um, clustering coefficient. The bottom graph is the shortest path length. And one thing that you can notice is that as you start rewiring, the shortest path length drops really quickly, abruptly, but the clustering coefficient takes longer to drop. So what this means is it takes longer to destroy the clustering structure than it takes to create the shortest path. So which means in this little bit in between zone right here, in this portion that I'm highlighting, the clustering coefficient is still very high. It's not as high as you started with, but it's still pretty high. But the shortest path is dropped all the way down. And so this is their theory of how a small world network forms. A small world network forms by taking a pretty clustered network, which has very high clustering coefficient, and just rewiring a really small portion of edges. And you only have to rewire a really small portion. It's like in the order of between 1% to 10%. If you just rewire like 1% to 10% of edges and create these random connections, now very soon you will get a really shortest path, average shortest path length for your whole network. So this is just one way to create a shortest path network. I mean a small world network, which is to rewire edges. So that's what is shown here in the top. You select a small fraction p of edges, and remember p needs to be just really small. Doesn't have to be long, because if it is too long, if it's too large, then you'll come to the other extreme where you'll also destroy the clustering coefficient. So you just want to keep it small, and you reposition one of the endpoints of these edges. The other thing to do is to not really rewire any edges, but just add some extra edges. So keep the ring network intact, just add some extra shortcuts, and that will also get you a small world network. It's very easy to do that. You have to make sure when you do this that you avoid self loops. Obviously, you don't want a node connected to itself. Many times it doesn't make sense. You also don't want multiple edges between the same pair of nodes. Typically, there's only one edge. So this is a really cool way because it not only tells you how to construct a small world network, it also obeys the properties that we feel are really important to be a small world network, which is high clustering and low average shortest path length. So remember this study was done in the 20th century, and we are now in the 21st century. So what these people did, Duncan Watts again, was after they wrote the first paper. And by the way, I want to mention that the first paper was published in Nature, and it was so small it occupied just half a column in Nature. And as you can see, if you get a paper published in Science or Nature, you made it in your career as a scientist. So this was a really cool paper that people were just immediately enthralled with and accepted. So they built upon this to publish a paper in Science, and here they did a modern day Stanley Milgram experiment. So here they did an experiment with email. So the experiment proceeded along similar lines. They picked people in multiple countries of the world, and some of them were designated to be targets. Some of them were given the initial email to send. So I will be asked to send an email to, let's say, the president of Colombia or somebody, right? And I have to guess who might know the president of Colombia. Who can I possibly send it to? Who might know the president of Colombia? So maybe I'll send it to one of my former grad students who was from Colombia, and then he will send it to maybe his dad who worked in the government, and maybe his dad knows the ministers, and maybe the minister knows the president, whatnot, right? So people gave these emails and they followed these things, and then they tracked the emails. It's a pretty cool experiment. It's so easy to do in modern with modern technology like email. It was so difficult to do in Stanley Milgram's time. And what they found was obviously there were a lot of chains, but only some of these chains reached their target. Remember, it was 20% in the case of the physical experiment. Here it was even lower. There were 384 chains that reached their targets, and the average path length was just 4. So, once again, if you view the world as a social network connected by email, it's again a small world network because it just took you so few hops to reach this. So now that we have these two notions learned, which is clustering coefficient and the small world network, we're now ready to start thinking about what do we want to do with all the ideas we've learned. We've learned quite a bit of vocabulary about network structure, and now we want to think about what do we want to do given a network. So suppose I give you a social network. What are the activities that you might want to do? And here are some tasks. We're going to cover them and study them in a little bit detail. You want to first talk about community detection. We'll talk about what that means. We'll talk about classification. It's a different type of task in network science. Link prediction, link analysis, and then viral marketing and outbreak detection and so on. So we're going to go through each one of these tasks, and it's important for you to understand what each of these tasks mean, what the input is, what the output is, so that next time you encounter a real life scenario in social media, you should be able to say, hey, that looks like an instance of community detection, or that looks like an instance of link analysis. That's really important for you to get the foundations straight here. So first, let's talk about community detection. And given a social network, so the nodes are people here, we want to try to understand what it means to be a community. Can we try to reconstruct or identify the communities underlying this network? And there are many other names for communities. People call them group, module, cluster, subgroup, and so on. But essentially, the way people define communities is it's a set of nodes among which the interactions are relatively frequent, right? So the example, the canonical example of a community is a clique. So a clique is when, let's say there are 5 people, they all seem to be connected to each other, or there are 10 people, and everybody is connected to 9 other people. But in reality, communities are not perfect cliques in real world. So maybe you will be okay with an almost clique, an approximate clique, or a quasi clique, and so on. So community detection has everything to do with looking at a network and trying to identify these groups, clusters, or cohesive subgroups, which need not be cliques, but essentially they look like they are cohesive groups. And the definition of community varies by application. So, given a full network, essentially I want you to output for me, okay, this network has 4 communities, and here are those 4 communities. Here are the nodes in each of those 4 communities. And there are many applications here. The first application is, this is simply a way for you to understand how the social network is laid out, how the interactions are organized. And understanding community detection is also important to other applications like optimization and so on. Suppose you want to reorganize your social network. Maybe it's a social network in your organization, and the edges denote who is talking to who, and maybe these interactions are suboptimal. So some consultant could walk into your company and say, hey, you know what, this is really not the way to run your company. I'm going to reorganize it for you so that the communities are much better formed and much more cohesive. And here's your new network for you, and so on. So there are many definitions of community. Here's a classical definition from an old book. This was again long before Mark Zuckerberg started Facebook in his Harvard dorm. Um, and here, the definition basically says a community is a subset of actors. And so it's important, this is often cast in the context of people. It's a subset of actors among whom there are relatively strong, direct, frequent, intense, or positive ties. So the meaning of all of these varies by the social network, but typically this is the connotation of what people mean by a community. And one keyword that is really important here is the notion of frequency. So if you're in Facebook, you might be connected to somebody, but maybe you never really talk with this person again. Maybe you connected when you were in a different city, and then you lost contact. So the frequency of connections is often important as much as just the fact that you have a connection with a particular actor. And the notion of interaction is really important. In this definition, a group of people without interactions is not called a community. So, the community of people traveling by the metro system every day wouldn't be considered a community, a real community, because they just seem to be happen to be in the same train at the same time every day in the morning, going to work and coming back from work, but they don't really seem to talk to each other or interact with each other. So, or the group of people waiting for a bus at a train station or something. So the interaction aspect is really important to be a community. So because interactions are important, you can use all the concepts that I have taught you so far, all the concepts of network science, and use that to formalize what it means to be a strong community or a strong group. So, any type of interaction between entities will provide you some interesting angle, context to do it. So, we're going to, when we talk about community detection, we're going to first use a lot of network topology information, similar to cliques and clustering coefficient and so on. And we're going to use that to create groups, and then we can potentially add other types of information to form communities. And once you form communities, you can use that as input to other types of tasks. So, as an example of how subjective community detection can be, so here's an example of a network, and you notice that the network is in like three parts, and we're just coloring it in different colors just to highlight that. But typically, when it's given to you, you don't know these colors. You just have a bunch of nodes connected by edges. So one thing you could say, for example, is each component is a community. That's a reasonable definition. But somebody else might say, well, I really don't think of a component as a community. The community needs to be densely connected. So I don't want to get the whole network like in the previous frame. I don't want to view this as a community because there seems to be some really sparse connections going on. I really want to focus more on, let's say, this, and call that a densely knit community. So what we mean by this is, do not get hung up on what we mean by a community, because different people have different definitions of community. You really have to think about what it means for that particular domain. In Facebook, the notion of community, there are multiple communities on Facebook. So defining community can be very subjective, and even for a particular system like Facebook, there could be multiple definitions that are suitable for multiple tasks. So once you find communities, one typical thing that people do is you can start using the communities to group the nodes and visualize them. So given a network like this, so you have nodes numbered 1 to 13 here, and this is sort of one particular network of how they're all connected. You can find groups, and you probably ran some community detection algorithm, which we will talk about. You'll find these types of groups, and then you can color the groups by their community membership. So nodes 1, 2, 3, 5 are colored in yellow, and nodes 6, 7, 11 are colored in cyan, and so on. So this is sort of one simple way to visualize communities and how their link structure is exhibited. Let's move on to another um class of problems having to do with networks. This is classification. So this is not so much about community detection. In community detection, you're given a network, and that's it. This is all you're given, and somehow from that, you have to use this information to find these colors and groups. In classification, you're given not just the network, like these people networks, but you're also given some other information in the form of class labels, which could be some sort of user preference or behavior. So, for example, Facebook probably does this to you, which you don't know, I don't know. It's going to classify you as, okay, you're a person who goes downtown to work, or you're a person who works from home, or you believe in recycling, or you don't believe in recycling, or you like a certain product, or you have a certain political affiliation, and so on. So people are given labels, which are membership in certain classes. And so, given a network and the labels of some of the people, some of the actors in the network, what we want to predict is the labels of all the remaining actors. We want to classify all the remaining people in the network who don't have labels. So, as a simple example here, here's again the same social network as before. Some of them are labeled blue. Blue means these are people who smoke. Some of them are labeled green. These are people who do not smoke. And then there are some nodes which are labeled black, which means we don't know. So you're given both the network and the label information, and you have to figure out a way to classify them. Again, this is something we'll go through in the course. We're going to do this, and once we do that, we're going to predict what happened to all those people who are black. So this particular algorithm is predicting that these two black nodes, 8 and 10, are actually smoking people, and these two nodes, 6 and 9, are actually non-smoking people, and so on. And 7 over here is also a non-smoking people. And the rationale, one type of rationale that these algorithms use is that people are influenced by the company they keep. And so if your friend purchased something, or your friend is a smoker, and lots of your friends are smokers, and maybe you're a smoker as well, so that's an assumption that they make. It may not always be true. That's a very simple assumption that these algorithms make, and use that to make predictions or forecasts or classifications. The other type of task in network science is called link prediction, and this is really interesting. So link prediction essentially says there are two nodes which do not have a link, which are not connected. Can you predict who or whether they are likely to get connected? So given a set of nodes in a network, look at the nodes that do not have an edge between them and see if potentially there could be an edge. They could get connected, and this is sort of how Facebook makes friend recommendations. So when Facebook shows you people you may know, this is really what they're trying to do. They're doing link prediction. The same with LinkedIn. When LinkedIn says, you probably know this person, they're making the recommendation based on a lot of things. They're first of all making it based on the fact that you people seem to travel in the same circles, or maybe they notice that both of you graduated from Virginia Tech in the same department in the same year, so you're likely to know each other, and so on. So link prediction is typically using network properties, both network overall network properties as well as node properties, to make predictions of who are likely to get connected. So you can also think of it as an edge prediction task here. So when you're given a network, you're going to potentially say, "Oh, here are some new edges. Maybe 2 and 3 are friends. Maybe 5 and 7 are friends. Maybe 7 and 13 are friends, and so on." So you make these type of recommendations, and that's a useful task again in network science. The other type of link analysis is just plain link analysis. So here we are not trying to predict links. We're trying to use the link structure uh, to impute some notion of importance to nodes. So you're going to look at a network like this, and you're going to use the notion of link structure to say, what, this network looks to be really important to me, or what, this node here seems really important to me. So link analysis is all about imputing importance, priority, weight, or strength to nodes based on the link structure. And there are two types of link analysis. Again, we'll talk about this in detail. One is called absolute importance, one is called relative importance. Absolute importance has to do with how important they are in the whole network. Relative importance has to do with how important they are in the local network. For example, I might be a big important guy in my floor of the building, but that's it. In the larger scheme of Virginia Tech or no, Northern Virginia, I may not be a important person at all. So there's notions of relative importance as well as absolute importance. And link analysis is one of the ways by which Google is said to use to rank search results. So their ranking algorithm is called PageRank. It's PageRank both named for Larry Page as well as the fact that they're ranking web pages. And these guys filed a patent long back describing how they use link structure to rank web pages. So pages are ranked by importance not only based on the content in these web pages, but also by the fact that other people seem to link to their pages. So if I'm linking to your page, then your page is probably important because I took the trouble to link to it. Um, so Google claims this is their secret sauce behind their algorithm. Between you and me, I really don't believe it. I think it might have been important in the early years of Google. Um, I really don't think PageRank is that important because most of the rankings that you could get by PageRank, you could get by some other measures as well. So if you're interested, I can get into it at a more detail. But PageRank, although it's very famous and it's the one that everybody thinks of when they say link analysis, actually has its roots in another search engine project at IBM called Clever, which uses an algorithm called HITS, which stands for Hypertext Induced Topic Search. And HITS is really can be considered to be the forefather of PageRank. Um, and in fact, they're really closely related. You can think of PageRank as a very special case of HITS. Um, so in that sense, HITS is a little bit broader and more general. So when we study link analysis, we'll talk about PageRank in detail. We'll talk about hits, and there are many ways of applying it. So even though Google uses it for web pages, you could apply it to the Facebook network, to the LinkedIn network, and so on. And in fact, there are a lot of papers where they have applied these algorithms on these real networks and found some very interesting properties. And then finally, we'll talk about the task of viral marketing or outbreak detection. And I already gave an example of viral marketing in the previous lecture, but if you recall, the idea in viral marketing is to talk about again importance of nodes as a target for marketing, not so much for their intrinsic marketing value, but for their network value, right? So people have different names for it. Some people call it social capital, and so I want to market a product to you, not because you will buy it, but because you will recommend other people to buy it. So a very good example is the publisher coming up to me. He wants to make an appointment with me as a professor, and he wants to pitch a book to me. And he knows the professors don't make much money. They're not going to buy the book themselves. So he's going to give me a courtesy copy of the book. But if I use my word of mouth and I recommend this book to all my students are going to buy the book. So he's approaching me not for my intrinsic value, but for my network value. I have a network. In this case, it's a network of me and my students. And if I recommend a product, he's thinking that my students will purchase the product. So it's good for him to market to me. And so viral marketing is about finding a subset of users to influence other people in a network, right? And providing incentives for this set of people, right? So you might provide something to me, and then they will in turn be able to market to others. So this is very prominent now in Facebook. There are people who have over the years accumulated a very big network of followers, and they will charge you some money to make a post on their page on Facebook. Uh, I remember, for example, when summertime comes, everybody wants to run a summer camp or the other for children, and there are pages hosting the summer camp catalogs. Each of them is going to charge you $250 or $500, and you're marketing to them not because they're going to join your summer camp, but because there are zillions of parents who follow those groups who will see that ad and potentially send their child to your summer camp. So this is the viral marketing problem. The reverse of this problem is what is called outbreak detection. In outbreak detection is sort of the reverse problem. You actually do not want something to spread. So a good example is like a disease, right? Or in social networks, you could think of it as fake news, or you can think of it as a rumors. So if there is a rumor, for example, that Ebola is airborne, which it is not, you want to control that outbreak. You want to control the outbreak of that rumor or fake news. So you want to figure out who should I target so that when they tweet about it, people are going to follow them and rest reassured that Ebola is not airborne. So these are people who can help either detect outbreaks or control the infection from spreading beyond it because they are influential within their network. And both these two problems are interesting when you have a limited budget. So if I have only $100 to spend, and with $100 I can potentially recruit four people in the viral marketing case. Who should these four people be? Who should I target so that they will be able to provide the maximum reach for me in the given network. So here's an example of how viral marketing will work. Um, if you want to do this viral marketing over this network with the minimum number of nodes, one of the things you could do is do some sort of greedy selection. So I could say, for example, I'm going to pick this node one because this person one seems to be really central to this subgraph. So I'm going to target this person one, and one, if he or she chooses to market my product, to retweet my post or whatever, it's going to reach all these other people who are connected to one. But once I select one, I should now move on to a different portion of the network, which is not covered by one. And that's difficult to do in the small network case, but you get the idea here. I'm going to now target eight. But once I target eight is now going to help me reach 12 and 13. 8 is also going to help me reach this node 9, which by the way I also already reached using one. But maybe if 9 is going to see it from two different people, both 1 and 8, maybe 9 will be more, coaxed to buy the product. So I selected one node here, I selected another node 8 here, and then I select yet another node here 7, which again 7 is going to market to 6 and then to 11. So with just three nodes, I have covered the entire network. And this is not a foolproof method. This is what is called a greedy method because I'm making these local choices as I go along, and there could have been different choices I take. But it's a very simple example of how you do this type of viral marketing. So to find a person who has some very high position in a smaller network, and then keep doing this iteratively. And it is also important to note that if you do this, it is not true that the nodes you will end up picking are the nodes with the high centrality scores. So remember, we talked about three types of centrality scores: betweenness centrality, degree centrality, and closeness centrality. The nodes that you pick here are not quite the same as the nodes with the centrality. So a good example here is 7. 7 is like some lone node which is sitting out here, which has only two other nodes. But you would really still target 7 because 7 is helping you reach other nodes that are not reachable by any other way. So when you do this type of selection, you have to really think of new measures, better measures to identify and reach your full network. Let me talk about a slightly different application of the same viral marketing, but now for disease outbreaks. So remember, in the case of disease outbreaks, the goal is to try to prevent the outbreak from spreading or to detect the outbreak. So the goal is, again, can I track a set of individuals and follow these people so that by following these people, I get a very good handle into the overall network. So there's this classical paper which came almost a decade back, which came up with this notion of social network sensors. And the idea in social network sensors is I'm going to follow these people, right? So if I give a network here, this is a full network. These are networks where the nodes denote people and the edges denote, let's say, friendship. I'm going to follow this person. I'm going to follow this person, and I'm going to follow this person, and they are my sensor. And I'm going to use these people as my sensors or my insights into the full network. I'm going to track what they're doing. I'm going to track whether they get infected, whether they fall sick, and so on. And I'm going to use them as sort of sentinels into the health of the overall network, right? And obviously, you have to get permission from people A, B, and C before you do all this stuff. But assuming you get approval from your IRB to do this, this is a useful exercise to take. So what these people did was they did an actual social network study. So this is not your fake social network like Facebook, where it's not clear that the notion of friendship means the same. So they went to Harvard. Well, they didn't really go to Harvard. One of the authors is from Harvard. So they went to Harvard. They recruited a bunch of students to participate in the study. So some 700 plus students. And they followed them for a full semester. and they're tracking these people about, did you get the flu, how sick are you, and so on. So every week these 774 students were tracked, and every week there will be a little health questionnaire that will be sent to them to say, hey, did you fall sick, hey, did you fall sick, and so on. And these people agree to participate in the study. And then after they're tracking their health, they started asking, uh, creating the social network sensor. And to do the social network sensor, they asked these people to name their friends. So they took these 774 people and asked them to name friends. So each person listed, some number of friends, and some of them obviously will have common friends and so on. So in total, they found a set of friends, which is 425 friends. And so essentially, the full social network is these 774 original people plus these 425 extra people, which together constitute the social network. And then they also took a random sample from the larger Harvard undergraduate student population, which was about 300 people. And so what they did was they tried to see how many people got uh, influenza during that semester that they were studying, right? And they used this random group, um, and tried to track this random group, and then they took this friends group and tried to track this the friends group. So what they did was, the x-axis is the number of days of infection. The y-axis is the cumulative incidence here. So as soon as you get the flu, you keep getting added to the bucket. So influenza just keeps getting increasing. This graph here is a daily incidence, which means you get the flu, and then after some time you get cured of the flu, so you come back. So the number of people who get infected with the flu increases and then drops, but here it keeps increasing because once you start counting them in, they're never out. So this is a cumulative curve. This is the daily incidence curve. And what is interesting here is they found these, the red curve is the random curve, and the blue curve is this friends group. I'm not going to get into the details of how they formed the social network sensor. There's some very interesting theory that they did, so we'll get to that. But what is interesting here is, if you look at the friends curve is a little bit shifted ahead of the red curve. So you can plot that here. You can see that here as well. The friends curve, which is blue, has the same shape as the red curve, but it's shifted a little bit to the left, which is really exactly what you want for a social network sensor. Because if you just follow these blue people and track when they are getting infected, their curve essentially happens a little bit ahead of the real curve. So when they get infected and the infection stops, you know that very soon this red is going to go up and then red is also going to start dropping. So this is a very practical example where just following a subset of people, and the friend network, is a much smaller number than the full group here, and it gives you this early lead time advantage, because what is really important is the gap between these two time series. And when you give that gap, you're now getting an early lead time advantage in knowing about the outbreak, when it's going to peak and when it's going to drop, and so on. So this is the same picture as in the previous slide, except now we're showing it in a sort of a ideal context, where the red curve is the full population, the blue curve is your sensor set, which are in some sense the most central individuals, and tracking them will give you a cumulative curve that is shifted a little bit earlier, and in the daily incidence curve, it's essentially the same curve replicated and again shifted leftward. If you've been watching this closely, the reason this social network sensor works is that there's a very subtle phenomena in effect, and it is often known as the friendship paradox, which means that the paradox simply states that my friends seem to have more friends than I do. I'm sure every one of you have felt like that. I have felt like that many times, I felt like the most unpopular person in a crowd, but my friends seem to be really popular, and that's why when you ask people in that Harvard study to list their friends, they tend to list these friends who are high degree, and so the people who are named as friends often are people who have high degree and who can serve as good censors. Now, this is called a paradox because it's really not true. It's really not true that your friends have more friends than you do, but it's true from an empirical point. And this is an example that came in the Washington Post. It came in the Washington Post Wonk blog, and this is uh, this is what they call an illustration of the majority illusion in social networks. So on the left here, you see a social network here, and the social network is basically a group of people here who are connected by friendship edges. And this blue color means that these people like to wear baseball caps, and this orange yellowish color means that they are against baseball caps. They don't like baseball caps. So if you look at this network, well, it's really clear. It's so obvious that the majority seems to be against using baseball caps. So they don't seem to be sports fans. They don't seem to like baseball caps. And so you would think that if this group were to come to a consensus, they would conclude that let's not use baseball caps. Let's just go with um, just uncovered heads, in real life. But what really happens in the social network friendship paradox is you have to look at it from the viewpoint of every person. So I'm taking each person at a time here. So I'm taking all the nodes here and I'm ordering them in rows. For each node, I'm listing their network. So there's a person who's colored yellow, and he has three blue colored friends. There's a person who's colored blue, and he has six yellow colored friend, and so on. So for each person, I'm enumerating their friendship network, and I'm picking the majority view of the friends. And if you look at it, suddenly the majority becomes the blue color. So most people are against baseball caps. This color is more popular. But when you look at the friendship network, the majority view now seems to be for baseball caps. And this is really important. And the reason it happens is because those people who are for baseball caps have very high degree. They seem to be connected to a lot of people as opposed to the people who are against baseball caps. So when you take these people as a sensor, they provide you a very distinct early bird advantage to how the overall network behaves. And again, this is assuming that the network behavior can be tracked with these types of sensor nodes. And people have taken this idea to a large extent, and it has been theorized. I don't know how much this is true, but it has been theorized that support for gay marriage and same-sex marriage really changed in the last 10 years or so because people seem to know somebody who was gay. So if you track, for example, the support for gay marriage over time, there's been a tipping point right around 2011, and at that point there were more people who had support and oppose. And when you interviewed these people and asked them why did you change your mind about support for same-sex marriage, almost inevitably the answer is they know someone who was gay or lesbian, and they felt that okay, I know these people, these are nice people, they should be allowed to have this right, and that's why I'm switching my support. So it's very similar to this. uh, Even though the majority may not be for baseball caps, they know people who have baseball caps and who like baseball caps, and so their preference based on the notion of networks could be very different from what the simple profile suggests. So all what this means, long story short, is that network structure is really important, and you can use network structure as an indicator into the overall status of a network, and you can also use it for marketing and influencing campaigns and so on. People have used this idea as a way to track events on Twitter. So, for example, there is a notion of social network sensors where it's not real people; these are Twitter handles. So some are real people, obviously, but some may not be people. It could be organizations or other entities. And so people have done these studies where they've taken a disaster situation like Hurricane Sandy or so on, and try to define these social network sensors so that by following them, you get a lot of insight into how the recovery process is progressing. And these are the people who send a lot of messages, who are well connected to the network. And by focusing on the subset of the people, you actually get a lot of insight, early bird advantage into the overall progression of dynamics in the network. So, what you know so far, we've covered a lot between last week and this week. You now have a very good idea of the static view of networks. We haven't talked about any networks in a dynamic or a growing sense. So these are static view. We talked about different types of networks like bipartite networks, cliques, planar networks, and so on. We talked about degree distributions, connectivity, density. About power loss, centrality, random graph models. And today you've learned a lot of new concepts such as clustering coefficient, small world networks, and now all these different tasks of network science. So you're now ready for your real homework, one assignment, and that should cover most of these concepts that you have seen so far. And together, you're now equipped to do a lot of analysis on social networks just by applying this vocabulary that we have seen here.